Okay, welcome everyone. This is my so, somewhat ad hoc but hopefully useful tutorial on how to use one of these little screens with the AVR chip that we're using in ENCM 369. And by the end of the tutorial, I'm going to show you how to print a W to the screen. And it's going to be a shocking, the amount of work that it's going to take us to print this W on the screen will be initially shocking to you, but hopefully will teach you a bunch of stuff about embedded design and how to get sort of peripherals working at a low level. And so just a quick look at my test setup here first. This very scary looking business on the back of my screen is actually just me connecting my trusty ADALM logic analyzer to the chip on the back of the display. So if we look, I've got these nifty little clips that clip onto the leads of the chip on the back of the screen, and that's because as part of this tutorial, I'm going to be showing you a logic analyzer waveform to kind of explain how things are working. Now, you don't have these little clips, or we haven't given you these little clips, and you don't need to do this, right? So the logic analyzer is just part of the tutorial, but it's not something that you have to do in order to use the screen. In fact, the electrical connections for the screen are super easy, and you can see it on the back of the device. You basically only have 4 wires that you need to connect: ground, VCC, which is 5 volts, that's easy enough, and then serial data, SDA, and serial clock, SCL. And serial data, or SDA and SCL, are standard inputs when you're working with the I2C serial bus, and I'll be talking you through sort of what that is and how to make it work. But in the back here, I've got my I've got my little ribbon cable connected to those 4 pins, and the SDA and SCL pins are just connected to pins PA2 and PA3 on the AVR, and I'll explain which ones you connect to when we start looking at the data sheet and some diagrams. Okay, so all right, somebody's handed you this screen, right? Let's say, at work or wherever, and said, okay, hook this up to this brand new microcontroller. And you're like, okay, well, how do I sort of get started with this? And of course, the logical thing is to just start doing some web searching. And sure enough, if you look at the manufacturer of this little screen, it's their the one I found was Freenove, www.freenove.com. The model name is LCD1602. And sure enough, the freenove.com had this helpful little tutorial zip file that I downloaded, and there's a full tutorial on how to hook things up. And we sort of look at this thing, and it's pretty kind of tantalizing. There's some diagrams. This, in particular, looks great. We've got like some diagram here, and especially this looks good to us, right? Like, this is, for those of you who haven't used it before, this is the Arduino, like, super simple development environment. It's got a little include file, and you just sort of give it an address, create an object, initialize it, turn on the backlight, print to the screen, and you're done, right? Super simple. The only problem is you're not working with an Arduino. And the libraries that have been written for the Arduino don't exist for your processor. And so you now have to dive into the details of how this thing is actually built. And you're not going to be surprised to hear me say this, but this is going to turn into largely an exercise in reading data sheets. And so if we look at the back of our device, our little screen, you know, it looks like it's kind of got like this sort of board, sort of tacked onto the back of it, right? It looks like somebody's made this little daughter board and put it onto the top. And I'm not sure if we'll be able to get it on the camera, probably not. But if you look closely enough at the chip, you'll see the numbers. I'll just look at my magnifying glass so I can see it. You'll see the numbers 8574T on the back of the chip. And you could maybe do a little bit of Googling around on what an 8254T is, but maybe you'll recall as we flip past it pretty fast, but there's a picture here of the PCF, 8574. That's the chip that we're working with. And we were like, great, this is the chip that we're interfacing with. And so if we find the data sheet for the 8574, it says it's a remote 8-bit I/O expander for an I2C bus. It's actually not an LCD driver chip. And you're like, okay, that's a little weird. Well, let's take a closer look to see exactly what this chip is. And I encourage you to sort of read through the introduction in the data sheet. I'm not going to do that for you right now. But here's kind of a helpful little diagram. So basically what this chip does is it's a serial to parallel converter. So basically what you do is you send 8 bits or 1 byte into this chip using the I2C, SDA, and SCL pins. And basically it takes that 8 bits and outputs those 8 bits on 8 parallel lines. And so this is just a thing that allows something with a parallel digital interface to communicate over I²C. And that's basically exactly what this LCD screen is. If we go back to the tutorial picture, we can see that our PCF 8574 connects to the LCD1602. So in fact, on the back of our LCD screen, we've actually got 2 chips communicating with each other. The first one converts I2C to parallel digital outputs, 8 of them. And those parallel digital outputs are connected to the LCD1602 with names like RS, RW, DB0, DB1, DB2. And so the next step in sort of our kind of detective work here is to figure out what all of these inputs mean on the LCD1602. Now, luckily, inside the zip file, the tutorial zip file from freenove.com, there was an actual data sheet for the LCD1602. And it looks like this. And it's if we take a look, and this block diagram is maybe a useful one to look at, we can see that basically our screen doesn't have an I2C input. It's got a parallel digital input. So it's got some control, it's got some control lines, E, RW, and RS. And then it's got 8 parallel digital inputs. So we've got a mechanical picture of the screen, and a bunch of waveforms, and then a whole bunch of other information. But if we take a look back at our diagram here, we can see that the names of these digital sort of parallel pins are described in the LCD1602 datasheet. Now, you might have said, wait a minute, if we go back to our screen datasheet, we have 3 control lines and 8 data lines. But we've only got 8 lines coming out of our I2C converter chip. So how does this exactly work? As it turns out, these little screens have 2 modes. The first mode allows you to use all 8 of these data pins plus the 3 control pins. So you actually need 11 digital I/O pins to interface to your screen. Or there's something called a 4-wire mode or a 4-pin mode, where you've got the 3 control pins and then you only use 4. The screen functions using only 4 of the data pins. And that's kind of nice because then that's only 7 digital I/O pins. So if you have, like us, only 8 to work with, you can still interface with your screen. So now, one of the things, and I've only worked with a couple of these kind of alphanumeric type El Cheapo displays, but I'm kind of noticing a pattern. I think that this whole like 4 versus 8 data pin kind of control interface is a bit of a standard. And the other thing that I notice is that the data sheets for the displays themselves basically copy a bunch of information out of the data sheets for the LCD controller chip, right? So typically the manufacturers of these displays will make the display, but they don't make the chip that controls the display. And so in our block diagram here, you can see that there's this control LSI chip, and then it basically connects to the actual LCD panel. Now, if you sort of read around a little bit in your display data sheet, pretty quickly it's going to mention the name of your driver chip. So here it's like SPLC780D. What's that? That is actually the IC that is put on your chip that controls the actual display. And it's always a good idea to find the data sheet for your LCD controller chip because it's a little bit more complete than the display data sheet. So that's what I did. I found it here. And sorry, I'll go back up to the top. So it's the SPLC 780D data sheet. And it talks about, as we were kind of saying, there's the 8-bit operation mode, there's the 4-bit operation mode, and basically this data sheet describes all the commands that you send to the LCD controller chip to make it display stuff on your screen. So obviously it's things like the characters that you want to print out on your screen. In our case, the letter W, but also it's kind of the control messages you would expect, like clear screen, whether or not you want to use one or both lines of the display. There's usually like a scrolling mode on these screens, so you can write something that's longer than the screen and it sort of scrolls back and forth. So all that kind of functionality is described in this data sheet here. Okay, so kind of our stage is set, right? So like all things that I'm teaching you, this is going to be an exercise in deciphering data sheets. And we now have the data sheets that we need, and we have an understanding, hopefully, of the overall kind of structure of our display. So we've got our I2C bus to parallel converter chip connecting to the LCD driver chip on our actual display, and of course, we also have our trusty AVR data sheet as well. And so those are the three documents we're going to kind of be working with in this tutorial. And so find those documents now, basically. And I've posted them on the D2L page, so make sure you've got them handy. Because basically what I'm going to do now is I'm going to start by talking about I2C, what it is, sort of serial communications, what's special about I2C. And once we've sort of established how I2C works, then we're also going to have to talk about how the LCD screen works and what commands you need to send to the LCD screen to get it working, which is also kind of not trivial. So we'll be swapping back and forth between data sheets. Okay, so a quick overview of how I2C works. Basically it's a two-line serial communication protocol, and the first line is the serial data line, or SDA line, and the second line is the serial clock line, or SCL line. And as the name suggests, the SDA line contains the data and the SCL line contains the clock, and it's relatively simple. A bit is placed on the SDA line, then the clock rises, and as the picture suggests, while the clock is between the rise and the fall of the SCL clock pulse, the data needs to remain stable. These pictures that I'm showing are from the 8574 data sheet, so figure 4. Now, the next feature of I2C is that there's a special start condition and stop condition that indicate the start and stop of a transmission. And so the start condition, as the figure suggests, is signaled by having the clock high and then having the SDA line go from high to low. And then the stop condition is again signaled by having the clock be high and then the SDA line go from low to high and then just be held there. And so these are the two conditions that indicate the start and the stop of an I2C transmission. And it's good to remember sort of the start-stop condition because the AVR datasheet talks about it when we're like configuring our code. This is just a picture of how you can have multiple devices connected to an I2C bus. And the way that this is possible is using addressing. So, the terminology I use now is main and secondary devices, because the old terminology is obviously very dated. So for the purposes of our little circuit, we have one main transmitter. So in general, I2C allows for bidirectional communication. One device is in charge of the device that is in charge of the bus is the main device. It can transmit and receive, but for our purposes, we will only be transmitting. So we're only going to be sending information to our secondary device, which is the LCD. So the AVR is our main device, and the LCD screen is our secondary device. And we don't have anything else on our I2C bus. We don't have to worry about it. But if we did, there has to be a way to direct transmissions towards, one secondary device and not others. And so all I2C transmissions include an address. So if we go down here, the address for our LCD is actually hard-coded within the chip to a certain extent. So there's two addresses here, one for the PCF 8574, one for the PCF 8574A. We have a 74, so this is not the one that we look at. And it's basically, you can think of it as a 7-bit address followed by a 0. This A spot in the transmission is the acknowledgement. This is when the secondary device acknowledges that it's received the transmission. And so the first 4 bits are hard-coded. And then these last 3 bits are determined by the A0, A1, and A2 pins on the, the 8574 chip. And so where are our pins, you ask? Well, if you look at the back of the chip, or if you look at the back of the LCD, you can see that we've got some jumpers here. And these jumpers, I'm just taking a picture of them. Oop. These jumpers by default are open. And so that means that there's pull-up resistors behind each of them, and these little jumpers would connect the bottoms of those pull-up resistors to ground. So if you short these, if you short these jumpers, you set that corresponding address pin to 0, and if you leave them open, the corresponding address pin is a 1. And so that means that the address of our screen is 0x27, because A0, A1, and A2 are all equal to 1. Now, down here is another kind of useful diagram. This one shows basically a full transmission. So always an I2C transmission starts with the address. And, well, actually, it always initially starts with the start condition. Then we transmit our 7-bit address. This read-write bit is set to 0. We have a clock pulse where we allow the secondary device to acknowledge our reception. An acknowledgement is indicated by a 0 bit. So as long as we don't see the SDA line rise up to 1 during this clock cycle, then we've acknowledged it. And then once we hit the device with the proper address, then it gets ready to receive our data. And this is where we just transmit 8 bits of serial data to our device. And those 8 bits are then just mapped directly to the parallel output pins of the 8574. So, and then you can, keep clocking in data. But for my example code that I'm giving you, I don't do that. So I just basically send the address bit, 8 data bits, and then the stop condition. Kind of inefficient, right? Because I'm sending an address, like 8 bits of address information for every 8 bits of data that I'm sending. And in theory, we could just keep clocking in data and then like program a full display of characters or something like that. But it doesn't really matter for this, honestly. Like, this is a pretty slow application. And so that's kind of an overview of I2C. And when we take a look at the code, it's important to sort of have these concepts in your mind, because then the code is going to make a lot more sense. Okay, so now we can look at a part of the code that I've created. So you'll have this is posted on D2L as well, just starting from the very top. I do use delay functions, which is, maybe a little lazy compared to how we've been doing delays in class. Like, we've been learning about using actual timers to be very precise about our delays. But for the purposes of communicating with an LCD screen, the delay functions in here are totally fine. So you need to define this FCPU. You need to create an FCPU definition equal to the clock frequency, which in our case is going to be 16 megahertz. I've got another defined statement here setting the display address, the I2C display address. And as we discussed, that's equal to 27. And just going straight down here, there's a bunch of stuff related to the LCD, which I'll talk about in a bit, but let's just go down to main. So here I set the internal clock frequency to 16 megahertz. Now, I skipped past it, but to understand the I2C code, you need to read the certain sections in the AVR datasheets, and I've given the sections here. You can have a look at the whole section if you want, but this is the most relevant stuff for the purposes of our display. You'll notice that in the AVR datasheet, it's not called I2C, it's called two-wire interface, or TWI, and that's basically a copyright thing. So I guess the actual copyright of the actual name I2C is a Philips semiconductor copyright, and so other people have to call it two-wire interface, but it's the same thing. It means the same thing. And I'll just call it I2C because that's kind of, everybody just calls it that. So going down here, we first have to set the baud rate, or the clock speed, for the SCL I2C clock. And this is described in the AVR datasheet, but basically this baud variable, it's essentially like a little counter. So it basically counts up to 67 and then ticks over the clock. And that's what this little formula is here. That's from the AVR datasheet. We then go to enable the AVR as the main I2C device, or two-wire interface device. And then we force the bus machine state into idle. And check out the AVR datasheet for these register definitions, as you do for anything. Now, I'm going to zip up to here, and this is the function that writes 8 bits to the I2C bus. The first thing we do, as I said, the way I've implemented this is I send out the address, then just 1 byte of data, and then I trigger the stop condition, and we go through this over and over again, so it's kind of inefficient. But writing to the main address register not only triggers the transmission of the address, it also triggers the bus start condition. And I left shift here to 1 because it's a 7-bit address, as we saw in the 8574 datasheet. We then sort of loop on an interrupt, which just pauses us until the address has been transmitted. Then we transmit our data byte, wait for that to be transmitted down here, then send the stop condition, and that's it. And again, going through the AVR datasheet, you can sort of look at the definitions for all of these registers. Now, here's a weird here's a weird thing. So I spent way too long getting this to work, and I had like a real sort of personal crisis because I felt like I'm teaching embedded design and I can't even get an LCD screen to work. And so I kind of felt like a failure for a while, because basically what I was seeing, I wrote all this code, it was all beautiful, whatever, and the display was behaving really randomly. So sometimes when I would run it, the W would appear on the display, but like at random times it just wouldn't. The display would be blank. And usually when some digital thing is behaving in a random way, it's because you're trying to make it go too fast, right? And so I thought, oh, okay, well, I must be, clocking out my I2C, too quickly or whatever. But I checked the data sheets. Everything seemed to be totally fine. Like I seem to be going like way too slow for the I2C chip, but for whatever reason, I needed to add this 1 millisecond delay, at least for my setup. And when I removed this, it didn't work anymore. So I don't know what's going on. I can only think that there's something weird going on with the display that needed, me to slow down a little bit more. But anyway, I added this and it worked fine. So yeah, that's basically it for the I2C code. Now, what I'm going to do is now sort of, so this is all we need to send an I2C command to create, those parallel IO pins, or to set those parallel IO pins that are connected to our LCD driver chip. Now we need to crack open the LCD driver chip datasheet to see exactly what those parallel pins should look like. Okay, so the next step, and I guess maybe just to recap where we're at. So going back to our kind of functional diagram here for what the LCD looks like. So we've talked about I2C communications, and so we know how to generate the serial waveform to go into SDA and SCL. And we know that this 8574 chip is basically sort of takes our serial data bits and puts them onto these parallel lines. So if we send in, a serial we have bit 0, 1, 2, 3, 4, 5, 6, and 7. So coming in serial, bit 0 is put onto P0, bit 1 is put onto P1, and so on. So we know that works, but the problem now is, what exactly does this device even want? What are these RS, RW, E pins? What sort of data is supposed to show up on these data pins? One thing I'll mention, I mentioned it earlier, is that we're going to be using the 4-pin mode for our LCD chip. And so only these four pins are going to be used. And NC is short for not connected, right? So you can basically assume that none of these are connected. And we're sending our data in just through this 4-pin mode. So you can look for that in the data sheet. And so if we look at the data sheet, and I'm not at all going to give you an exhaustive discussion of what's in the data sheet. That's for you, right? So you need to do some reading of a lot of reading of the data sheet and get familiar with it. But basically, in the data sheet, it gives sort of a recommended sequence of commands to send to sort of get the screen working. And this is the sequence that I basically implement in the code. So you set to 4-bit operation, you send some commands, you turn on the display, you set the entry mode, and then finally you write the letter W, which you have seen in my video that I was able to successfully do. Now, this, again, these devices are like, wouldn't it be great if datasheets were perfect, but datasheets, like people, are not perfect. And so this isn't actually the whole story. So if you go to the LCD datasheet, it gives you a similar but slightly different suggestion for how to initialize the screen. And critically, it gives these 3 extra commands before going into this sequence, which basically resembles, what I just showed you. So I'm going to take these 3 commands, but I'm not going to do exactly this. Once I get to this point, I'm going to go back and basically implement this sequence here. How did I arrive at this? Trial and error, literally, right? Like I just sort of, tried different combinations of this stuff and then finally got it to work. So I've saved you a bit of headache there, hopefully. So yeah, so these are the commands, and if you look at them, more closely, you'll see that this is the setting for the RS bit. This is the RW bit. Here's our 4 data bits. But what about the E bit, right? Because there was an E bit on that little diagram. E is for, I think it's short for enable, and it's basically the clock pulse that clocks data from the parallel lines into the LCD driver chip. And so if you go way down, I think it's like kind of more at the end. Yeah. Oh, no. Yeah, way at the bottom. Here we go. Here's the timing diagram. And these are always super important whenever you're doing this kind of, bit banging type stuff where you're just writing, data to parallel digital I/O lines. Basically what this diagram is telling us, and you can look in the datasheet for what these particular timing values are, but it's basically saying that the RS line and the RW line has to be stable before the enable line goes high, and then you pulse the enable line and it goes low, and that basically clocks the data in. Now, in this diagram, it suggests that you can, you've got the rising edge on E, and then you've got a little bit of time here before you have to put your data on your 4 or your 8 data bits. In our case, we're only using 4. But what I do in my code is I actually set RS, RW, and the data. So I sort of set the data out here, and then I pulse the enable bit. It doesn't really matter. Like, you can set the valid data before you pulse the enable bit. So that's what I do in my code. So this is kind of at a high level how I implemented the code, and then we'll go and we'll take a look at the code for those details. Okay, so going back to the code here, we've got this, or I've written this LCD write function, and this basically sends a 4 bits or a nibble of data to the LCD chip, sets the RS line, sets the RW line, and also turns the backlight LED, or the LED backlight of the display, on or off. And so this first little bit of code here, I create the bits that we're going to send to our 8574. And the data bits are the 4 most significant bits, so I just shift them 4 positions up. RS is the least significant bit. RW is the second least significant bit, the second least, I guess. And then the LED on bit is I guess, the third bit. And if you look at that diagram in the tutorial PDF, you'll see that this is where this corresponds to the 8574 bit that's connected to the LED input on the display. So I construct the bit, or to construct the 8 bits, I send that out over the I2C bus. And so this sets the data lines RS, RW, and LED. And then I'm just going to pulse the E line. And so the E line is, the E line is bit 3. LED is bit 4. So the E line, I set it high just by taking our existing data and setting that bit high. I retransmit the data with the E line set high. Then I zero it, and then I send the data again with it low, and that basically just pulses the E bit. Now if we go down here, I've got basically those 3 commands from the LCD data sheet, followed by the sequence of commands from the LCD driver chip data sheet that I showed you. And you can just sort of look at these values and then look at the data sheets and sort of cross-reference it. But basically I sort of initialize the screen, and then finally I write the letter W to the screen. Okay, and as promised, here's my logic analyzer waveform. So this top line is, this top line is, yikes. This top line is SDA. This is SCL. Now, this is too zoomed out for you to really see the I2C waveforms, but they look basically like the diagrams we worked through earlier. This line is RS, this is RW, this is E, and then this is D4, D5, D6, and D7. And so the first command that I send from the first command that I send in the code corresponds to where I've drawn this vertical line. So if you remember, we're sending 0, 1, 1 or 3 to the chip, and so the least significant bit is 1, second bit is 1, and then these two are 0. The next command is the same. The next command is the same. And now we get into the more closely spaced commands that, again, you can see in the code. So, whoops, I'm trying to get rid of that. So this is the first command. This sends data values of 2 or 0. Whoops. 0, 0, 1, 0. 0, 0, 1, 0. 0, 0, 0, 0, and so on. And if you pause the video and you sort of trace through this diagram, you can see each one of the commands that I send to the screen. And like I was saying, this is not you don't have to use the network analyzer, or sorry, the logic analyzer. But I just wanted to show this because I used it a ton while I was trying to figure out, what was going on with like my timing. Was it messed up? Because like I figured I was overclocking this thing, and it's really something to keep in mind. There is a little video on that I posted on D2L talking about how to use the logic analyzer. And as you work on your design projects, just kind of remember this, because this is really nice to be able to sort of look at a whole bunch of parallel pins. I mean, it makes your circuit look a bit maybe a bit shocking like mine did, but yeah, it's really nice. And you can ask the text, maybe they even have some of those little claws that you can use to sort of grab some of your individual pins. And so anyway, this basically is it for the tutorial. Now, obviously you've got a lot more work to do, right? You want to print more than just W on the screen. You're probably going to be constantly refreshing the screen. Maybe you want to use both lines of your display, and you're going to be printing all the letters of the alphabet and all the numbers. So but the data sheet is there for you, right? So this is the kind of the framework that you can work with. And this is, like I said, kind of a pretty rough, hacked together kind of tutorial, but hopefully it does, it did illustrate some of the ideas around how I2C works. This is like a super important, common, like serial bus that's used to connect to sort of simple sensors and simple peripherals. And so if you work in embedded design, you're going to be using I2C a lot. And yeah, hopefully this was useful for you.